台大物理系陈恒宇教授。陈恒宇教授是我们系最年轻的教授，是我们的青年才俊，明日之星。那么，而且他研究的专业领域是超弦理论，据说研究这个理论的人都是要3头6臂。对，我刚好也是研究这个理论。那听学生说上他的课都要非常专心，因为内容非常有挑战性，所以请大家等一下专心听，然后随时有问题都欢迎大家提出来。那我们现在欢迎陈恒宇教授。
So first I would like to thank Amy for the introduction. And I think like a few years ago, I think about like 7 or 8 years ago, I remember sitting in one of those lecture rooms and listen to similar kind of lecture, like very excellent lectures. So it was I think it's very honorable for me to come back and give this set of lectures and hopefully trying to introduce to some of you something new and something quite close to my heart. So, so I was told that there will be 5 hours of lectures, and the aim is trying to. Okay, okay, ma'am. So the aim is trying to introduce you a subject called integrable systems. So I guess it's fair to say that over the past 20 to 25 years, many of the major kind of breakthrough in the theoretical high-energy physics is tied to kind of emergence of certain integrable systems in various kind of physical situations. So for those of you who are interested in high-energy theory, that you may know that topic like matrix model or topological strings from 20 years ago, or well, 25 years ago now, in fact. Or, for example, a subject called Cyber-Witten theory, which is dealing with 4-dimensional n equals to supersymmetric theory. That also has a very close tie with integrable system. Or more recently, integrable system also emerges in the study of the so-called ADS-CFT correspondence, whereby, well, one can actually obtain, for example, exactly a scaling dimension of various chiral operator in the conformal field theory, like, for example, Professor Gao and Professor Huang, Professor Chen was talking about yesterday, that in terms of critical phenomenon, that a lot of those critical phenomena are described by various kind of CFT, and one of the most important physical quantity in a conformal field theory are to do with the scaling dimensions for various kind of operators in a theory. And those scaling dimensions generally can receive quantum corrections, and it's generally very hard to obtain an exact expression for those scaling dimensions. However, in a very special setup, sometimes called supersymmetric, certain class of supersymmetric field theory, one can actually apply the idea of integrability to obtain the exact value for those scaling dimensions. And even more recently, that scaling dimension is actually to do with a 2-point correlation function, for those of you who have some knowledge of quantum field theory. But more recently, that the idea of integrable structure has also emerges when you consider a higher point correlation function, namely the various kind of scattering amplitude in the supersymmetric field theory. So it's actually a very important, I guess, important thing in the theoretical high-energy physics over the past 20 to 25 years. So that's why I choose this topic to kind of introduce you to hopefully to all of you. But however, the idea of integrability is actually not something only emerging very recently, but rather it actually come up like from the time of Liouville, like I think like 200 years ago. Liouville was I mean, basically when you study quantum mechanics. So, when you study classical mechanics, and it's only more recently that the idea of quantum mechanics come in, and you actually study the idea of quantum integrability instead of classical integrability. So, I think the best way to actually think about those different kind of integrable systems is actually they are like an exact toy model, which is something you can actually obtain exact information from. And as a series, we do like exact info. We basically want to simplify. Well, what do we do as a series? Well, we try to come up with toy models so we can understand the real world a little bit better. And then we try to add the various pieces and bits to actually bring our system closer to what we actually try to aim for. That's what we usually do. So you should really view this various kind of integrable model, just like in quantum mechanics that you learn about simple harmonic oscillator, where the exact spectrum of your system is, you can know that like, for sure. And then, well, you do know that most of systems don't really behave like a simple harmonic oscillator, but something more complicated. But however, at least if you can simplify, or at least approximate your system into various kind of simple harmonic oscillator, then you do have a sort of physical understanding of roughly what's going on. So, and then you try to see if there are better ways, like for example, putting on a computer, putting on a lattice, various kind of ways to obtain better understanding. So that's actually one reason why people study this kind of integrable system, which also, by the way, also emerges in the study of critical phenomena. So, I guess another sort of very strong motivation. So I was told that in the audience there are various mathematicians as well. I think the study of integrable system also have a beautiful connection with, for example, study of Riemann surfaces like algebraic topology and geometry. But furthermore, they are, for example, also connected with the study of elliptic functions or various kind of characteristic polynomials, things like Macdonald polynomial, Jack polynomial, etc. And in fact, those various kind of very interesting functions, they actually appear as kind of eigenfunctions in the kind of quantum integrable system. So hopefully, toward the end of this course, we'll get to talk about some of those. So I was told there are 5 hours if typhoon permits. So the plan of the lecture would be that I will spend, I think, the first couple hours. So I guess go to lecture 1 and 2. I will try to begin by introduce you integrability in classical mechanics. So classical integrability. Is this size okay? Oh, by the way, don't worry about copying down everything in the notes, because I will make the notes available on the school website, so you can download it after each lecture. So for the first couple lectures, I will try to introduce a classical integrability, and then, I think in Thursday's lecture, I will talk about introduce you to quantum integrability. And I will particularly focus on something called a spin chain, or a method to solve those, this quantum mechanical system known as spin chain using a method called algebraic Beza-Enza. So I guess I would say boys 3, 4, 5, and then towards the end, given some luck, I will try to mention, application of integrability in, theoretical hydrophysics. So at least that's the plan, and we'll see how it goes. So I do have a tendency to speak faster and faster, and my reading to get more and more hard to read. So do interrupt me if you find it hard to follow, and do ask questions, and do stop me if my reading stops, being readable. Okay? Good. So is the size of the writing okay? Everyone fine with it? Okay, very good. Okay, so it's summer still, even though we are here. So I would like to start with some very gentle introduction, or in fact, to some of you, will be like a reminder to classical mechanics, and to help us set a notation and various kind of terminologies, and in particular, try to serve the mathematicians in the audience. Okay, so, and I would give some reference. So those are actually excellent lectures, I think, for more advanced students, I think final year undergraduate, you can already pick up and read those review notes. So, and also books I mentioned. So one book which I prepare my, heavily used when I prepare my lecture notes, is an introduction to classical integrable systems by Olivia Babylon. And for those of you in NTU, this is actually on the web by Cambridge University Press. So it's an excellent book. You should really try to pick it up. And then there are a couple of good lecture notes available on the internet. One of them is again with the name Integrable System by Dubrovin. And I think also Novikov is on it. So this one for Russian. This is slightly more advanced. Or maybe just to do with they are Russians. So, and the third one is a set of notes given by somebody in Cambridge. So also of the same name by Maciej Dunaski. So those are kind of like a text I use quite heavily, and you can find, well, so there's no way I will be able to cover everything certainly not in this book. But for those of you interested, do try to pick it up. I think you can actually start reading it based on your knowledge of undergraduate physics and mathematics. Okay. So those are the references. So what's a natural starting point when we study classical mechanics? Well, so in classical mechanics, usually we describe a motion of a dynamical system by specifying, say, a point in a so-called phase space. So, specify by a point in a phase space, and we usually by a point in phase space at any given moment of times. And so phase space is basically a even dimensional. So what would be a better way to put? So do you all know about phase space, or do I need to briefly explain this? For those of you who doesn't know phase space, raise your hands. Never heard of it. Okay, fine. It's a very simple idea. It's basically that in classical mechanics that we usually describe by Hamiltonian formulation of classical mechanics, we describe the system by its position. and the momentum. So your phase space is simply a so they are even so there is an even dimensional vector space which spanned it out. Basically, the coordinate of this vector space are simply given by the position and momentum of a certain given particles. So, and the indices here, I here run from 1 to say n. So you can imagine that we can have well, okay. So usually, what physicists would call this indices as a degree of freedom. But for those of you not familiar with the knowledge, with the terminology, then you can simply imagine that, say, in a one-dimensional system, that you can specify the motion of a particle that by its position and its momentum, and every single particle carrying one momentum and its position. So if you have n particle, then you do have a kind of n sets of n pairs of those Q and P's, and we usually say this as having n degrees of freedom. So, and the phase space is simply, it's a 2n dimensional vector space spanned out by Q and P's. And so if you have a system with n degrees of freedoms, then we specify its motion or its dynamic by, say, at any given time by a point Q, I, and Pi in the phase space. And basically, we usually describe the time evolution of this particular dynamical system by studying its trajectory as time evolves in the phase space. Okay? So we can actually express, so in this first two lectures, I'll use Q and P to denote the position and momentum of various kind of particles we are studying. But however, we can also describe various other kind of dynamical variables. So we can really think about the dynamical variables of the system as functions such that the f will map, so I give the phase space in notation m. So it's really a function that mapping m across a real axis, which is simply our time coordinates, into basically a real value. So it's really a function of both q, p, and time. Okay? So for example, your energy, your angular momentum, your or even your position or momentum itself, they can all be regarded as a function of both Q and P on the phase space. And I hope that's very apparent. So, and given two functions or dynamical variables, let's call it, say, f and g's on the phase space M, then we can define the so-called Poisson bracket. By the way, you can actually ask the question in Chinese, there's no problem. I can try to reply in Chinese as well. Okay. So we can define the Poisson bracket between the function f and g, which is given by the following. So as a simple exercise, you can show that well, actually, I included in the notes, that's fine. So how many of you have not seen the Poisson bracket before? Well, then you should pick it out from your classical mechanism lecture notes. So I think that's very good. Okay, so, and there's a very important functions which live on the phase space. That's something called the Hamiltonian. Which basically governs the time evolution of your entire dynamical system. It basically tells you how the trajectory should actually move along in the phase space. And the point is that, so let me just give it a name H. So the time evolution of various dynamical variable in your system is simply given by the Poisson bracket. So the dot here simply means d by dt is given by a partial derivative if f actually has an explicit time dependence plus the Poisson bracket as defined over there of the function f itself with the Hamiltonian. Okay? So for most of the situation, we'll be dealing with the case where f does not have any explicit time dependence. So we'll be just looking at the following equation. In particular, if f, so think about this bit off. So in particular, if f equal to either the position or the momentum, then we recover the familiar Hamiltonian equation of motion. So write it up once for all. So, which are set of first order differential equation in time, but generally h can be a complicated function of both p and q. So actually solving it is actually quite a difficult task. Even though we do know that basically the solution of those equations are simply determined, once you specify the Hamiltonian, actually just determined by the initial condition t equal to 0. And basically this trajectory, basically how basically the time dependence of p and q basically determine how say how the your dynamical system actually evolve along a certain given trajectory in So I hope this is kind of somewhat familiar to you. I mean, it's not totally foreign, right? Okay. So, so this is aimed just to set the notation for the following discussion. So as a good exercise, and I encourage you to do if you do not realize this is what's going on, is that to show that if you treat the phase space as a vector space, then you can define a volume element and so on. And to show that the volume element basically the volume element in the phase space delta V is given by it's actually conserved. Oh, I should just define, sorry, the conserved quantity, sorry. In case you don't know, that conserved quantity F is simply given by the fact that F dot T equals to 0, which implies by the time evolution equation we write down just now, it simply implies that H, the Poisson bracket with F equal to 0. Okay? So, and the exercise is simply to show that the volume element in the phase space is actually conserved under time evolution, i.e. it's invariant, under, say, small time changes. So how many of you done this exercise?
Sorry, I proved this 资源 just I use the linear 资源 can 我讲中文好不好？
可以啊。
我用利比的定理证明它，我需要证明利比的定理吗？这就是利比的定理吗？
Yeah, sure. I mean, that's fine. That's right. So you basically this is Liouville theorem. That's right. But you can actually prove it without knowing it. 你可以证的时候，你可以不需要知道。
啊？
你一开始证这个时候，你可以 you don't need to know about it.
OK， 我可以用最少的 information 来证这个东西。
Yeah,
你是这样。
Absolutely. All you need is Hamiltonian equation.
OK， 谢谢。
对，你们其他有人有证过这个 exercise 吗？有证过的举个手好了。What happened to classical mechanics nowadays? 我先出来证一下好了。Okay, but do try this exercise, and this is quite important exercise to do. Okay? So, good, but hopefully otherwise it's just setting up the notations. So let me just give one quick example. We're doing fine. Okay, we're good. Any questions so far? 有问题吗？ Too obvious.
问题，也许是我给一个phase，就是像空间，然后它的哈密托尼人是唯一的吗？这个问题
Of course not. Well, I mean, it's invariant. Well, okay, so do you mean like in terms of a particular coordinate, 还是说？
就是说我之前在念的 paper 里面，就是在时间是不变的时候，哈密托尼人其实它是可以差一